Let's try this one just for now. So we have a triangle ABC, and B is on segment BC. And XD is equal to XD. So yeah, we draw the perpendicular bisector BD and CD. And those are X and Y. I don't know if it's worth drawing these points right here, so I'm just going to avoid it for now. T lies on XY, so I'm just going to draw these to show it's isosceles, but then we want to see where does the perpendicular bisector of AD meet XY. We call that T, and we want to show that as D moves, T lies on a fixed line. All right. I'll draw these two and hide a couple things. So as we move D, we want to show T moves on a line. All right.
I will immediately say a couple things I know about this configuration.
Okay.
So intersect ABC, that circle with AXY.
Okay.
Then that intersection point is the reflection of the D in XY. Also, circumcenter of ABC lies on AXY.
The circumcenter of ABC. Okay. So that means that this is a kite right here.
I don't remember how to prove that thing with circumcenter, but this reflection is easy by angle chase.
It's just an angle chase. Because this angle XEY, well, it's probably very easy to, it's easy to show that that's XDY. But yeah, showing that these are the bisectors, it's probably just an angle chase. Yeah, because angle EYX is 180 minus EAX. Well, let me think about that.
It is easier to prove it when you take E as the reflection.
Okay.
Then you will have that X is circumcenter of BDE and Y circumcenter of DCE, and you will have all the angles.
Okay. So you show that X is a circumcenter of BDE and Y is a circumcenter of CDE, and then that solves the problem. Okay. So I wonder if the ratio XT over TY is always the same. Can we say that like does a spiral similarity take T to D? Let's see. I think that might be true. Oops. So YTE and CDE. No, it's not true.
Can we maybe draw the locus of T?
Yes. So yeah.
There should also be a tool where the perpendicular bisector is.
A tool.
Xt over ty indeed looks
the
like
last
a
one.
constant.
Xt over ty looks constant.
Yeah.
I didn't know about that locus tool. Interesting. Okay. So yeah, if it's constant, oops. I didn't know about that locus tool. Thanks for showing me that. So yeah, we have to use that TA equals TD somewhere. You know that dy equals ye. You know that dx equals xe. And we also know, basically we know that TE equals TA. So FT is perpendicular to AE.
How do we know that TE equals TA?
Because TA equals TD, and then
Reflection. Yeah, I get it.
oh yeah, it's a reflection.
Also, I don't know how to prove that F lies on AXY.
So yeah, we'll try to see how we can prove that.
I think I can show that T moves with degree like at most 5, which is maybe a little much, but yeah, we need 1.
Okay. So like, yeah, let's see if we can solve it without moving points. Like I feel like there should be a solution that doesn't use that. So we can kind of figure out what this line has to be, because we could let D equal B and then D equal C, and then kind of figure it out from there if we really wanted to. So yeah, I might try that. If D equals B, then so we take the perpendicular bisector. Yeah, basically we take the perpendicular bisector BC and we try to see where it meets AB and AC. And then so yeah, we can figure out what that line is, although I'm not sure if it'll be that useful, the condition. So basically, I think it's the line through the midpoints of BG and CH. We draw BG and CH, and we take the midpoints. So I think T will lie on that. So yeah. I don't know how helpful that is, but maybe it is. So yeah, we could say show that T lies on IJ. Oh wait, that doesn't look true. Maybe I did something wrong here. So D moves here. Oh, T is not going to be the midpoint of that. T is going to be the intersection of the. Okay, so that would make things a little more complicated. So really what you have to do, you have to draw the perpendicular bisector of AB. So see where it meets BG. Then you would have to draw the perpendicular bisector of AC and see where it meets CE.
Okay, I found something useful.
Okay.
That locus line of T would be parallel to tangent at A to ABC.
Okay. So let's draw the tangent.
So basically that would mean T is like an anti-parallel.
Ah, that locus is an anti-parallel. Okay, that's useful. So yeah, I don't know how helpful that is. Oh, this almost looks like a Gauss line, kind of, because if you consider, let's say you consider AGKB, then I is the midpoint of BG, J is the midpoint of HC, and then the midpoint of AK would have to be on this line too. So basically, if you draw the midpoint of AK, then we want to show that TL is parallel to the tangent. Yeah, okay. So yeah, I can delete I and J and all this other stuff that I added. Basically, yeah, if we draw the midpoint of AK, then we want to show that TL is parallel to that tangent. Interesting. I probably just used the Gauss line to figure out something that could have been much easier, but yeah. Okay. So the tangent at A, like you said, it's like an anti-parallel. So yeah, I don't know if some medians might be helpful here. Oh, wait. Does TE? Oh, we already said that. TE equals TA equals TB. So T is the circumcenter of ADE. Well,
Oh, I think I've solved the problem.
okay,
And didn't use that point K.
okay.
But it still remains to show that F lies on this circle. But let's just say it is true for now.
Okay.
We intersect FT with the circle, the small one.
All right. Oh, and it looks like these concur, right?
Yeah, they do. So, as I think it is an angle chase to prove that those concur.
Okay. So you let it intersect at G and then you show that this angle
Is tangent, yeah.
is tangent.
Yeah.
Okay.
So we have that angle GYX is GAX, which is ACB.
Okay.
And also, similarly, we have the GXY is ABC. So we have GXY and ABC are similar.
Okay.
And also, we have that the circumcenter of AXY lies on this line, GT.
Okay. So the circumcenter.
Yeah. So basically, this proves that XT or TY is constant, which is in the end isn't really important. But just because when you intersect AF with BC, you would get like two same like corresponding points.
Okay.
But you could intersect this with the circle. It is not just that important with actually intersect both.
Okay.
So FT or FG is also constant, since it will always be equal to JI or JA.
By the similar figures, yeah. Oh, yeah, I see
Yeah.
what you're saying. Yeah.
And G lies on a fixed line, which is tangent from A. So you could just take a homotopy at F to see that T lies on a fixed line.
Okay. So G lies on a fixed line because it's always on the tangent. So basically, by a homotopy at F, since the ratio FT over FG is constant, then T has to lie on a fixed line. Okay. All right.
Let's just see now how to prove that F lies on AXY.
Okay.
But it doesn't look like something which should be that hard.
Yeah, it feels like something we've done before. Let's see. Yeah, I'm thinking about it. Basically, yeah, we're saying as we move D along BC, those points are always going to be so yeah, we want to show fxb plus fyc is 180. We know that fb equals fc. So it's kind of like we want to show that when you put together triangles fxb and fyc, we want to show they make a cyclic quadrilateral because one of their sides are equal, fb and fc, so you can like glue them together. And we want to show that when you do that, it's cyclic. And yeah, the question is, yeah, how do you glue them together? So it's like if I rotated it, it's like if I rotate the triangle, then I want to show it gives a cyclic quadrilateral. Let me try something. I'm trying to use a lot of signs because we just need to show sine bxf is sine of fyc, and sine bxf over bf is equal to sine fyc over fc. So then we just need to show, let's see. Oh yeah, I think it might just be like the law of sine. So we need to show sine of xbf over xf is sine of ycf over yf. And that's the same as sine of xaf over xf. And we want to show that sine of fay over yf. Oh, I'm just going in circles. Yeah. This is interesting. Yeah, it doesn't seem like it should be that hard, but I don't know. Yeah, we need to show f lies on that circle.
How about we just say this is well known even though we don't know how to prove it?
Okay. I mean,
that is the smartest move, right?
is xf over fy equal to bj over jc? If that's true, like does the spiral similarity, so well, let's see. Yeah, we could just say that. But yeah, I'm just curious what the proof is. So let's see if we can.
Why don't we just keep working on it? Like, I don't think it's not that hard.
Yeah. Let's see. Yeah, so BJC is similar to XFY. But can we prove it if we don't know the circle exists? That's the thing. Yeah, there must be some kind of trick. But yeah, I could type up the rest of it. Might as well call this O instead of F. So OX and OY are like Chevians and AOB and AOC. So maybe if we let EX and EY meet the circle, it might help. Try that. Oh, EX and B aren't collinear. That's a good point. What if we did this? What if we draw the circumcircle of OYC? And basically, we want to show, I wonder if we draw this point right here, if OXB is congruent to this. I don't think so, because I don't know for sure, but like we want to show there's a point on this arc which is congruent to OXB. So like OBX is OAB. Yeah, I don't think these are congruent, but I'll check. It's 28.4.
Oh, I think I've proven that O lies on AXY.
Okay. Okay. Let's see. Oh, I heard you for a second. Now you're muted.
I think I was lagging, right? Am I lagging?
Do you think you were what? Oh, sorry, you're muted again.
I think I have a proof, but I'm not too sure. And it uses that xt over ty is constant. I don't know if we already have that.
Okay.
We don't have that if O doesn't
Oh,
exist.
okay.
Oh no, looks like Khan got kicked off. Let's see. Oh, he's having bad internet. Oh well. Right as he was about to get it. Okay. Now looks like he's rejoining. Hey Khan. So
Hello?
Hey, I can hear you now.
Okay, so I have proven that O lies on AXY.
Okay.
Okay, so let E, so we'll be using the point E. So we label E as the reflection of D with respect to XY.
Okay.
So you can hide a small circle and keep circle ABC.
Okay. But so, oh, because we kind of already proved that that lies on the circumcircle. So,
Oh yeah, so you can just keep it.
okay.
So we know that the reflection of D across XY lies in the circle.
Mhm.
And we have XE is equal to XD is equal to XB. So we know X is the center of that circle.
Yes.
And we know that angle, since we have angle EOA is double the size of angle EBA.
EOA is twice EBA. Okay.
However, EXA is also twice of EBX.
Oh, because XE equals XB. I like that.
Yeah, and that's it.
All right. So I will write up the solution. So all right. So let O be the center of ABC. C. And so first we're going to show, well, okay, so E, so let AXY intersect ABC at E. And then, so we could show by an angle chase that E is the reflection, because, let me think about that.
No, you take E as the reflection. It is easier that way.
Okay. Let E be the reflection of D over XY. And then angle EXY, we want to show it lies on the circle ABC. So
Angle XEY equals angle XDY equals angle XAY.
okay, by an angle chase. So XEY, so angle XEY equals XEY equals angle XAY. And that means that AEXY is cyclic. And then also, we want to show that it lies on the circle of ABC, right?
You can do that by calculating angle BED, which is half of BXD. And similarly for CED.
CED. You said BED and CED?
BED and CED.
Okay.
You have the circumcenter, and that's why you get you can get those angles.
Okay. So BED. Okay. So X is the circumcenter of BED and Y is the circumcenter of CED. Okay. Okay, so XED plus YED, we can calculate that each of those, and basically if we could show that it's angle A, well, okay, so we want to show angle BEC. Okay, we want to show BEC as BAC, but BEC is XEY plus BEX minus CEY. So we have angle BEC is equal to angle XEY plus angle BEX minus angle CEY. And those should cancel because BEX is EBA. So CEY is YCE. So this is just angle XEY. Which is XAY. So BEAC is cyclic. And then let's see. So let OT intersect. Oh, then we want to show O lies on it. So
Yeah, just show that EOA equals EXA.
EOA is EXA. So angle EOA. So EXA. We can calculate that in terms of this angle. So EOA, we want to show it's EXA. Give me just a second. EXA. Okay, so we're going to use that this is isosceles again. So EXA is 180 minus EXB. Well, we could just say EXA is twice angle EBA. Yeah, sorry, I'm losing it. So angle EXA. My boss is just making me too nervous. So EXA is to EBA. I'm going to blame it on him. It's twice EBA. And which is angle EOA. And that means that EXOA is cyclic. And then similarly, EYOA is cyclic. And that means EXOYA cyclic. And then once we know that, let OT meet that circle at G. And then, so GXY is similar to ABC. Well, first we want to show its tangent, which should just be an easy angle chase. Let me check the chat. All right. move this stuff up. Okay, so we want to show that GA is tangent. Well, OT,
Angle OAG is 90.
okay, so we're defining G. Are we defining
OT and circle again?
Okay, so we're defining it like this, where OT meets the circle, but then we know that this is 90 because I guess, yeah, like we don't know yet that it passes through the center, right? Is it obvious that OT passes through the center of the circle? Oh, because TA equals TE. That's why. Okay, so I forgot about that. So TD equals TE, TE equals TD equals TA. And so that means that, or I'll say it the other way, TE equals TB equals TA. From there, we know that TG, that basically proves that OG is a diameter. Diameter, and that means that angle OAG is 90. So GA is tangent to ABC. Okay. And then so a homothety, basically the ratio, so yeah, GXY is similar to ABC by an angle chase. Let me just think about that for a second. Yeah, because GXY is 180 minus GAY. So I'll just say GXY is similar to GBC by an angle chase. Okay. And T corresponds to I, T and O correspond to I and J. So J and this similarity. And that means that GT over TO equals AI over IJ equals constant. So by homothety at O, T lies on the line parallel to AG. say t moves with OT over OG equals JI over IA. And that solves it. All right. So pardon me for my slowness and my brain not working, but sounds pretty nice solution. All right, so we have about 45 minutes left. This one is probably a little bit hard. This was an inequality. We could try this, or we could look for another problem. The only thing about this, so I'll show this one to you guys. Sorry, I'm just having trouble maximizing it here. I wonder if there's a keyboard shortcut to maximize stuff. Because it's not working for me right now. Let me see. So if I go to this one, yeah, let me maximize that, but it won't let me maximize this. Maybe I'll try putting in another window and seeing if it'll let me do that. Let's try it now. Yeah, something weird about, yeah, it wouldn't let me maximize that. But I'll show you guys this problem. Oh no, it won't let me. It wouldn't let me paste it. Okay, let's try this one more time. Copy. I don't know if it's actually copying this or not. Otherwise, I could go to the Discord and just copy it from there. Let's try it. Yeah, it won't let me do it. Okay. It's riddle 251. I'll have to scroll back a little bit. Or we could just search for another problem, but it looked kind of cool, so I'll show it to you guys.
You don't have to scroll, you just use a search.
Search.
Discord.
I'm close enough. But yeah, next time I'll use the search. Okay. There we go. All right. So we have a triangle ABC with circumcenter O. And here's where it gets tricky, because you draw the circumcenter. And then you draw the circumcircle BOC. You want to draw a circle tangent to AB, AC, and BOC. So I don't know of a great way to draw a circle like that. Unless you guys have an idea of how to do it. So other than just, so for now I'm just going to guess. So yeah, I could do a guess for now. And it's easier if this is like obtuse. You could try to make it like really obtuse. Let's see. Maybe something like that. Maybe there's a better way to do this. Let's see. Actually, that looks not so bad. So it's like the two are tangent at a point Z. And we call the points of tangency X and Y. And we can reflect A over XY. And we want to show that ZA prime is the bisector of BZC.
I think we can construct the circle by using an inversion.
Oh, really? Okay.
Because using inversion with power 1/2 AB times AC, so
Okay.
the circle BOC will be transformed into the in circle of ABC. I mean
Okay.
the Euler, the 9-point circle.
Oh, the 9-point circle.
Yeah,
Okay.
and we know that that inversion takes AC to AB and takes AB to AC.
Okay.
So it must take the circle beta to the circle that is tangent to ABAC in the 9-point circle, which is the in circle of triangle ABC by Feuerbach theorem.
Oh, that's really clever. Okay, so it takes that little circle to the in circle is what you're saying.
Wait, it can be the X center too, because the X center also tangent to the 9-point circle too.
It should be eccentric since
it must be
these two are externally tangent.
Okay. So all right, so I'm not even going to draw the 9-point circle. Basically, but I could just say by Feuerbach's theorem, it would take that circle to the X circle. That's what you're saying, right?
yes.
Okay. All right, let me delete point E.
This really is a great insight.
Yeah. It almost seems like whoever made this problem definitely was intending to do this root BC inversion. Okay. So let's draw the X circle. And I remember your trick. I'm going to use it to draw the X center. There we go. Actually, I don't even know if I need to draw the other one because I already have the angle bisector. But this is the X center, and wait, yeah, that's the X center. And this is the X circle. Okay, whoops. All right. Let me hide stuff that I don't need. It's not so messy. Okay, so the inversion takes that little circle beta to the X circle.
And also,
the
I
X
think you
circle
should
scaled by 2?
draw.
Oh, sorry, what were you saying, Kyle?
I think you should draw the 9-point circle because that inversion takes z to the tangency point of 9-point circle and the x center, the x circle.
Okay. All right.
I'm confused. Isn't it all scaled by 2? When we have just a normal root BC inversion takes circle BOC to the 9-point circle scaled by 2, right? At A.
Is it scaled by 2 or do sorry, I'm not sure. Let me think about
No,
it.
I mean, if we use root BC inversion at A, then O becomes the reflection of A over BC. So the circle OBC becomes the 9-point circle scaled by 2 at A. Right?
Let's see. So if I reflect A over BC, yeah, so you think it might have to be scaled by 2?
Yeah, I think so.
Actually, yeah, it's 1/2 AB times AC, like I said in the beginning.
Oh, okay. So it's not just a root BC inversion, it's a root BC over 2 inversion. Okay.
Yeah,
So
it is.
yeah, I remember you said that.
I just don't know how to call it in in specific terms.
No, it's all good. It's all good. Okay. So K. So here we wanted to show ZA prime was the bisector of BZC. Let's see what that turns into. So B and C switch. Z goes to K. And so we have basically angle BKC. Do we know where A prime goes to?
I think you can construct point Z accurately, 100% accurate, by using the property of the inversion. So maybe we can work better. I don't know. It's just up to you.
Okay, so yeah, how do I draw a circle with radius root AB times AC over 2?
I think if you just type in circle where the input goes, you can do like point and then radius.
Okay, circle with center A, and then radius, let me just try it out. Okay, AB times AC. Do you know, is it SQRT, or do you know how I do square root?
I'm not sure.
Okay.
SQRT might work. If it doesn't, maybe just raise it to the power of 1/2.
Oh, yeah,
Actually, you don't really have to construct it that way. You can just find a point Z such that AIZ and AKB are similar, and AZ and AK are just orthogonal.
Okay. I'm going to try it really quickly, see if it works this way. So AB times AC over 2, and then raised to the 0.5. And then this might just be less work. So if I invert K about the circle, but then I have to reflect it. Okay, so then I reflect it over AF, and then I could get like the exact point. Interesting. All right, so let me Let me hide this Z prime. Actually, I could delete this circle. And if I reflect K over that line, then I would get what Z actually is. This should be Z. So I want to circle I want to draw the center of BOC, and I want to see where it intersects. So I get rid of point B. And if I see where this intersects that line, that would be the center of the circle. So D would be the center of it. And then I could draw that perpendicular, and then I could draw that circle. All right, and then this would be Y, and the other one would be X. And then I'll make it look nicer. Okay, so let's hide this. This is the line DZL. I don't even really need that line. And this circle I don't need. All right, so I think, let me delete these. I think that's good. I could probably hide this point. Although maybe I'll want to use it later, so. Protassov lemma? What's that? Sorry, Ryan just messaged me.
Yeah, for problems that include those like tangent circles, you maybe can use Protassov lemma.
What is Protassov lemma?
Okay, so let ABC be a triangle with RIB is in center, and then you take an arbitrary circle passing through B and C, and wait a second, let me just summarize it.
Okay, so you have like an arbitrary circle through these points and the end center, the end circle.
No, just be an arbitrary circle. Then let another circle tangent to ABAC and tangent to that circle, to the arbitrary one.
Okay.
And then the tangent point, let the tangent point be a point, let's call it X or something.
Okay, I'll just pretend this is tangent. Yeah. Okay.
Then the line through T and the in center of triangle ABC bisects angle BTC.
Oh, really? I didn't know that. That's an interesting lemma. Is it hard to prove, or I never heard of that before?
Do you know the T-ball circle?
Yeah.
So yeah, we prove it using the T-ball circle. But so okay, let's go back to the original problem when you call the in center of ABC. Can you label it?
All right. And then let me see what it called that circle. Center, center of K1. U. Okay.
Then ZU ZU bisect angle BZC by the Protassov lemma.
Okay. So ZU bisects BZC.
Sorry, how do you spell the lemma?
Let me see. So it's I'll put in the chat.
Thanks.
Problem. So okay. So ZU bisects BZC. And oh, it looks like I accidentally hit A prime. So we want to show that A prime lies on that. So if I reflect A over XY, oh, maybe A prime is U.
It must be, because the problem is equivalent to that.
It has to be. Yeah, you're right. So we need to show that the in
This is
center.
obvious then with Protassov lemma.
So it's obvious that the in center is a reflection of A over XY.
Maybe we
Maybe
can
not.
use inversion to prove that. I don't know.
Yeah, I was thinking this. So
Oh, actually, I think it must follow from root BC inversion. You see that in center and X center swap under root BC inversion.
okay. So it's actually a root BC over 2 inversion, right? That
Yeah,
we
but
did before.
you take some homotopy, right?
Okay.
Somewhere you take homotopy.
So Ryan just mentioned that to me, BUZX is cyclic. That's an interesting observation.
That fact is used to prove the Protassov lemma.
Oh, that BUZX is cyclic.
Yeah.
Interesting. Okay, so let's see if we can apply inversion. But yeah, it seems very clear that whoever made this problem wanted to use Protassov, I would guess.
Yeah, I see that Protassov lemma would follow easily if we knew BUZX is cyclic.
Interesting. Yeah, because then it's by symmetry, UXB is going to be UYB. So yeah, then it would follow if we knew that.
Han, could you repeat exactly which inversion takes this XYZ to X circle?
Sorry, which to which? Can you repeat?
XYZ to X circle.
It is the root BC, root AB times AC over 2. Let me just type it in the chat.
But when I drew in root BC over 2 inversion, and I think it didn't take BOC to the 9-point circle. If I took root BC inversion and then took homotopy with factor 1/2, then that would be it. Okay.
All right. Sorry, my boss keeps texting me, but I'm okay. But fill me in on what you guys just said. Did you guys figure something out?
I'm pretty sure this can be, this will follow from inversion, but I cannot see exactly how.
Okay.
That the reflection is the in-center.
All right. Invert about a circle, yeah, and then reflect over the angle bisector BAC.
Yeah, that's what they mean. Like in Vietnam, we use like inversion with power instead of, reflect inversion about circle with radius. So I kind of mess up with the terms right there.
Oh, it's okay. Like I understood you when you said it originally, like AB times AC over 2 and square root and then reflected.
Han, I drew in what you said, and you need to take a homotopy with scale factor 2 to get from X circle to that XYZ.
So I think Ryan.
Actually, Michael.
Yes.
Like I think it is true because Michael constructed it that way, so it must be true.
Oh, with the AB times AC over 2 and the square root.
Yeah, we are still, thinking about that, but I assume that it is true because I've used it like many times.
Yeah, that's how I constructed.
Like,
that's how I constructed this point Z. But I think Ryan has a solution, so he sent it to me directly. But yeah, just yeah, Ryan. So I don't know if he realized that it was a direct message. Maybe he wanted it to be just directly to me, but he found a solution. So let me see. I'm gonna put it. I'm gonna type it here and see what you guys think. So. Okay. So U is the in-center. So we mentioned as part of the proof of Protassov. So yeah, this is the proof of Protassov, but then he's saying it's equal to CYU. Which is so yeah, BXU equals CYU. We don't even need Protassov to do that. So U's on the angle bisector. So and X and Y have to be like symmetric across the angle bisector. So by symmetry, we have BXU is CYU. But then we're saying that's also half of BZC. Yeah, which is half BZC, which is a half of BOC, which is BAC, which is half of BOC, which is BAC, which is 2XAU. So since BXU is 2XAU, oh yeah, so XAU is isosceles. Interesting. So yeah, that does it. So XA is XU and YA is YU, so U equals A prime, and then that solves it. Yeah. Okay. But wait a sec. Okay, so we define U. Yes. Okay, so I think this works, right? This looks like it works. I wonder if we need now I'm wondering if we even need Protassov. Well, we need to know that this is cyclic and then it follows quickly. But I think this does it, right? EXU.
Actually, the part where we have, yeah, actually you kind of don't need, but yeah, it's just similar to Protassov, but it's not. We don't really need to, call it Protassov. It's just angle chasing.
Yeah,
But
it's just,
the fact where BUZX and CUZY, you have to prove it using T-ball circle, I think. It's not
T-ball's
really easy.
theorem.
Yeah.
Okay, so we really didn't need to construct. So drawing the X circle helped like get the exact point Z, but we didn't really need these, like, it just helped to draw the diagram, but it's not actually using the proof, right? Those circles.
Yeah, they're just used to construct a diagram.
Yeah. Interesting. That's still a really good fact to know. Okay. So to prove BUZX and CUZY are cyclic, we have to use Thibault's theorem, is what you're saying.
Yeah. So do we have time to prove it? Yeah, we still have like 15 minutes. So
Okay. Yeah, that sounds
I think
good.
we can prove it. Right.
All right, let's see if we can do it. Okay, so I'll just leave the X center here for now, but yeah, I don't know if we'll actually need it. So yeah, Thibault's theorem, if I remember it, it's like you have a triangle and a Chevian and you draw the two end circles of these, and then you draw another circle. Oh no, you draw the circles, the mixed linear circle that's tangent here and then here, I think, right? So, or curvilinear. So curvilinear is like when it's tangent to MQ, QN, and this arc, right?
Yeah.
Okay, so these are
And then the theorem says that it will have the common tangent within circle, right?
Actually, it says that can you just draw like the circle that is tangent to the. I know that you can just draw it like so that we can easy to observe it.
in circles, or just like try to make a guess, kind of.
Yeah, trying to make I guess. Yeah.
Let's see.
So the T-ball theorem says that RS passes through the incenter of M and P.
Oh, yeah, that is not too hard to prove.
So RS passes through the incenter, and this would also pass through the incenter, right?
Yeah, I
Yeah,
think I have an
it's the
idea
same
how to
thing.
prove it.
Okay.
So we would add in the midpoint of arc NP.
Arc NP, okay. Let me move this up just a little bit.
Also delete this second circle to the right.
This one.
Yeah. Also, it is interesting. I proved exactly this thing on my JBMO team selection test.
Oh, really?
Yeah.
It's funny.
So by homotopy, TR and B1 are collinear.
Yes. Because the tangent at B1 is parallel to PN. And
Yeah, and you intersect RS and MB1, and we want to show that it is the incenter.
you intersect RS and NB1.
Yeah. MB1.
Oh, sorry. So yeah, I didn't need to draw that.
Now add in the the center of this little circle. Okay, if I remember correctly, there is some cyclic quadrilateral here. Maybe MTWS. But it doesn't look like that in here.
But yeah, I didn't draw it. I didn't draw everything perfectly, so it could always be. Could be my drawing. Let's see.
Try to make it better.
Okay. Or we could use this theorem to draw the circle perfectly.
Yeah, we could.
I think it's pretty close to that. So.
And maybe MSVW is cyclic. Draw the perfect diagram.
VSMT is cyclic.
VSMT.
It is because we have, it is due to an angle chase. Hold on.
Yeah, it is an angle chase, but I just couldn't remember which circle was cyclic.
Yeah, this one is kind of complicated.
Okay, but so it's VSMT in general. So yeah, I could draw the end circle.
Yeah, we don't need the center then. I just thought it was the cyclic was with the center.
Yeah, so actually, like on my channel, I have the video on mixed linear end circles, where I prove that something like this is cyclic. And I think the same proof works for curvilinear, because I think I saw it, like there's the book, A Beautiful Journey Through Olympiad Geometry. And I think the proof is like really the same thing in both cases.
I suggest we just apply this one to the Protassov lemma.
Yeah. So yeah, so this is like the proof that XDZU is cyclic. Or I'm sorry, BUZX is cyclic. That's basically what this.
Actually, yeah, there's one more step before that. Wait, let me just.
Okay.
Can you let AB meet circle BOC at a point?
Yes.
by the generic version of T-ball, XY meets XY passes through the X center of BA1C, I think.
Oh, really? Okay.
Because in this situation, the small circle XYZ, it is outside of the circle BOC, so there will be a little difference. Like in the T-ball theorem, the small circle is just it's inside of the big circle. So
XY passes through the X center.
which one? I think this is
Yeah,
with respect to A. Yeah.
Interesting. Okay, I'm gonna delete this diagram, or are you guys okay if I delete this?
Oh no, just keep it because it is the T-ball theorem.
Okay. Okay.
Yeah, and by the proof that me and Stefan stated, that point lies on BOC. I mean ABC C1 is cyclic.
Okay.
And then
and then you're thinking maybe that could help with the proof that that's cyclic?
yes, because like in the original T-ball theorem, we have ABC and C1 is cyclic.
Okay.
And also,
so also, like, if we took this point, yeah. So basically it's like you're saying that this circle passes through D1 and this circle passes through C1, CUZY.
yeah, that is my point. Like you have to construct C1 and D1 before showing that BXZU is cyclic.
Okay, so it's like we know. So which of these points do we know lies on the circle, and which do we have to prove?
By T-ball, we know that B, D1, X, and Z.
Okay, so we have to show that U
So,
lies on it.
Yeah, so the rest is an angle chase, and I don't remember how to do it, but I don't think it's hard.
Interesting. So let's see. So yeah, we have to show U lies on that circle. What do we know about U? We know angle XUA. Okay, so we want to show BZU is BXU. Send, please. Okay. So BXU, that's equal to angle A. Can we show BZU? Yeah, somehow we have to show U lies on that circle. Yeah, my brain is just not, it's not English. Even if it's another language, I don't mind. That's what I love about geometry.
You
Like,
can just,
or what?
I think you should just write down what we have done and then just, you know, at the end, you just leave it for the viewer or something.
Okay. Sounds good to me. So, like that. Whoops. Okay. So I'll just say like, let X, Y meet ABC at B1 and C1. Prove BUZX is cyclic. Let XY meet ABC at D1 and C1 by Diebald's theorem, or really by the proof of. Using angle chasing, and we have D1x UB is cyclic. I'll just say, see if you can show that U also lies on this circle. All right, this is cool. So there's a theorem. I've never seen this theorem before, but it sounds very useful. So
I can write down the proof. Like I translate from Vietnamese to English for you guys, and I put it in the server, the Discord server.
Sorry. Okay. So. All right, so yeah, you'll post it on the Discord server. That sounds good. And I think I am going to stop here. So for everyone watching on YouTube, thanks for watching and helping support my channel. And thanks to everyone who participated today and shared their solutions. So I feel like I really learned a lot. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.